will always be with us. I would also like to recognize the presence of our Vice Principal, Sir, Professor Kamal Kumar Gupta, IQAC Coordinator, Dr. Aditya Saxena, Sir, DBT Star College Scheme Coordinator, Dr. Indrakant Singh, Sir, respected faculties from our college and from other colleges of the university, present dignitaries, researchers, and student participants. The Department of Physics has created enrichment in excellence and in the college by achieving high repute in academics as well as in co-curricular activities. Enriched by the legacy of renowned teachers in the past, the department is proud to have committed faculty which excels in research and teaching. Our department also inculcates scientific and experimental spirit in students. Now, without wasting much of your time, I would like to request our respected Vice Principal, Sir, Professor Kamal Kumar Gupta, to address the audience with his words of encouragement. Over to you, sir.
Am I audible? Did you hear me?
Yes, sir, you are audible.
So good morning, one and all present here. I feel proud and privileged to welcome today's keynote speaker, eminent physicist and researcher, Dr. Chandra Shekhar, senior scientist at Max Planck Institute of this chemical physics of solid. Welcome, sir. This welcome is on my own behalf, at the same time on the behalf of Deshbandhu College. I welcome the DBT Star Coordinator, Dr. Indrakant, IQAC Coordinator, Dr. Aditya Saxena, senior faculty member, especially Dr. Uday, all the faculty members of physics department, all that of Deshbandhu College and from other colleges. I welcome all senior faculty members and other faculty members of Deshbandhu College. I feel privileged to welcome all the participants, students, ladies and gentlemen. And in fact, it's really a wonderful moment that physics department is starting an international talk series. And to hold an international talk series, I give credit to COVID, who have taught us to organize many of the international events online. I remember 2 years back, we hosted an international conference in India, and there one of our participants was not willing to, was not able to make it to visit, and he was asking if we can arrange an online talk, but we are feeling so handicapped that time. What is online talk and all these things? But probably, if I see the positive aspect of COVID, then I'll say certainly that this is an achievement. We have many more frequent international talks, and not only this, we can approach right now all over the globe. So global, the entire world is a small global village. On this occasion, I like to congratulate the teacher in charge, Dr. Kakuli Bera, teacher in charge of physics department, and also convener of Physics Society, Dr. Pankaj Singh, for hosting such a wonderful, to envision this international talk series and to organize this. But of course, I cannot forget students and all the faculty members are the pivotal role in hosting such events. The title, the topic of the talk is Not Yet Finished Journey of Hall Effect. And I know all the faculty members would be certainly benefited, and also all the students will get an insight of such a latest research in physics. With this, thank you again and welcome again one and all. Thank you.
Thank you, sir, for your kind and motivational words. A good teacher can inspire hope, ignite the imagination, and still a love of learning. With these words, I would like to invite our respected teacher in charge of Department of Physics, Dr. Kakuli Vera ma'am, to welcome and introduce our guest speaker. Over to you, ma'am.
Thank you, Dr. Monica Sharma. Very good morning to all of you. I, Dr. Kakuli Bera, on behalf of Physics Department, Deshbandhu College, University of Delhi, welcome our Principal Sir, Professor Rajiv Agarwal, Vice Principal Sir, Professor Kamal Kumar Gupta, distinguished speaker, Dr. Chandra Shekhar, all faculty members from all the departments, and all participants, students in this international lecture series on recent advances in physics. Today's topic is Not Yet Finished Journey of Hall Effect by Dr. Chandra Shekhar. It's my great pleasure to introduce Dr. Chandra Shekhar to all of you with his brief academic record. Dr. Chandra Shekhar is currently working as a senior group leader at Max Planck Institute at Dresden in Germany. He received his MSc and PhD degrees from BHU. He worked on superconducting materials for his PhD degree under the supervision of late Professor O.N. Srivastav at BHU. Dr. Srivastav has been credited to synthesize iron-based superconductor in India for the first time. Later, he joined Max Planck for his postdoc, and since then, he is in Germany. He is currently working in the broad area of solid-state physics, including fundamental aspects of topological, magnetic, and superconducting materials. He has shown his research capabilities through his research articles in various journals such as Nature, Nature Materials, and Nature Communications, etc. Dr. Shekhar has credit of publishing more than 100 papers, in which 17 are in Nature Journal only. He has H index of 79 and I-10 index of 77 and 6,870 citations, which are self-explanatory of his research contribution. Now, it's my great honor to welcome Dr. Chandra Shekhar for his talk on Not Yet Finished Journey of Hall Effect. Welcome, sir. Over to you, sir.
So, thank you very much to all, and very good morning from here. So here is also very good morning. Now it's 6:10 o'clock in the in the morning. So, and I'm very happy to listen a long introduction about me. So such I'm it's a very pleasure to present this work, and I'm very thankful to all the faculty members and all the students. And I also thanks to especially Ashwini, who is my colleague, who invited me and suggested such a topic, who might be interested to all faculty members and all the student. So without any delay, let me start, and just let me share my screen, then we can go and start my presentation. So I think is it now visible to everyone?
Yes, sir, it is visible to you.
Okay, and also this is start to moving. Okay, so so as you know, as in introduction, my topic, which one I'm going to present now, is not a finished journey of Hall effect, and everybody know that most of the physicists and chemists know the Hall effect, which was discovered earlier, but there is so many versions there, but still we are hoping some new version in near future. So actually I'm working here in Max Planck Institute, and which is in field of the chemistry and physics. By name, you can see this name is written as Max Planck Institute of Chemical Physics of Solids. So physics and chemistry involved in the form of solids every in all over the my institute, and I have this so personal my group web page. You can go there and you can find recent activity. You can contact me by email. So as I said, this Max Planck is earlier known as a Kaiser-Weill Society, which was established in 1911. But up to 1942, they changed their name and now become the Max Planck Society. So in earlier society, there was 15 Nobel laureates, and also in new society, which is known as Max Planck Society, now is 22 Nobel laureates, which was also included from 2 Nobel laureates from last year. One is from the chemist, one is from the physicist. So Max Planck Society is very big society which work as a government institution, but in working like a independent from the government. So we have up to now like 80 research institute, and within the country we have 77 institute, and 3 institute is outside the Germany, and 2 institute is belongs to US, and 1 institute in situated in China. So in when you calculate this percentage of the overall institute, we have 50, nearly more than the half of the faculty members and research member is outside the Germany, which is we call the international researcher, and less people is from the Germany. So we can say that the whole society is like a very nationally recognized society, and we always welcome the all over the world people. So, so basically this institute is belongs to completely research institute. There is no academic like a master and bachelor degree, but we have a academic degree which is start from the PhD. So in each institute we have a PhD recruitment in every year through the International Max Planck Research Institute. We have a very good website. We can say in IMPRS website, each institute has one IMPRS website where every year we advertise the PhD position, and we welcome the master student to join the PhD. So as a through the Max Planck Institute. So these are the basic important point about this society and from the this Max Planck Institute. So let me talk about my topic of the Hall effect. We know the electron has 2 things mainly, is charge and spin, and we know this both can responsible for the current. Charge is responsible for the electrical current, which is known nowadays very popular, but spin is also responsible for the current. This is we call the spin current. So electron has 2 things, charge and spin. I'm going to show you some more slide where we can see the effect of the charge and effect of the spin both. But we have also some different type of material. Normally we can say magnetic material. We have non-magnetic material. Magnetic material we popularize like iron, cobalt, nickel, and steel. These are the magnetic material where spin is more responsible for their property. But non-magnetic material, we have like aluminum, gold, copper, where charge is more responsible for their property. So, so basically, electron is every material, but depending upon this type of material, where the spin is responsible, somewhere the charge is responsible. So these are the introduction that I want to say. This type of material we have when we do some experiment. So depending upon this type of experiment, charge is responsible and spin is responsible. What type of measurement we are doing, this is the aspect of our experiment. So let me go through more detail. So we have different type of material. We have 3-dimensional, 2-dimensional, 1-dimensional, and 0-dimensional material. So depending upon the dimensionality of the material, independent of the this type of material, magnetic and non-magnetic, this charge of this electron, this charge can be confined inside the material. If you have 3-dimensional material, so charge is freely to move and free to move everywhere. Like here in the down, we can see the energy dispersion curve. Here you can see corresponding energy dispersion curve. In 3-dimensional, we have parabolic like dispersion, means electron behave a parabolic behavior. But when we go in 2-dimensional, when we make a sheet and confine the motion of electron or charge carrier in 2-dimensional, so energy is not varying in 2-dimensional like parabolic, is energy is varying like a stair. So we just by making device are simple in such a way where we cannot let go the electron in another direction. In for example, in 3rd dimension, the behavior of electron will change in dimensionality. When we have a wire, so it behavior of electron change lot. So electron can go this charge can go in only one direction. And we when we have a particle like a nanoparticle where so electron doesn't move anywhere, so energy is like, so dispersion is constant. Dispersion means the velocity of electron or motion of electron is constant. It doesn't allow to go anywhere. So this spectrum means balance band and this conduction of this material will change. So depending upon the dimensionality of same material, one suppose material is 3-dimensional and one material is 1-dimensional. So dimensionality is can change this conduction of the valence band energy and conduction of the this conduction energy. It can change. So I want to say so same material, we can change the behavior of electron itself without doing any external entity. But we have also some external entity where we can stimulate the this property of material by changing the temperature, by applying the electric field, or by applying the pressure. We can change the behavior of charge particle or motion of the charge particle or spectrum of the charge particle inside the material. So just now I'm going to talk about the what happened when we apply the magnetic field inside the material. And so that is discovered. So Hall discover a property by applying a magnetic field inside the material. And in 1879, which was very old, but nowadays is various variety of that effect occur and exist. So up to 2013, we know all this property has been discovered, but there is more versions are there according to prediction. So this timeline is given to discovery. So we have two things. One is prediction of the theory, one is observation of the theory. So this timeline is given the observation of the theory, and for example, is some effect is predicted earlier but discovered later. So this timeline is discovery of the realization of the their effect. So let me go point by point. So Hall effect, which start the journey in 1879. So what is the Hall effect? When we put a material in a magnetic field and pass a current, so we have a extra voltage which is extra developed voltage, which is perpendicular to the perpendicular to the magnetic field and current. This is the extra current which is developed by the magnetic field. So that is voltage we call the Hall voltage, and what is the origin of this Hall voltage is the Lorentz force. So we have a charge carrier inside the material which can deflect. So depending upon their positive and so negative charge, depending upon their deflection is depends. So according to right thumb's law, this we can find the direction of the deflection of charge carrier. So one extra voltage developed perpendicular to this magnetic field and current, that is we call a Hall voltage. So that Hall voltage is discovered by the Edwin Hall in 1879, which is called the Hall effect. So how do we measure this Hall effect, which is very simple and very useful in material perspective? And how do we measure? So we just measure a 4 probe, which is measure the resistivity basically, and apply a magnetic field and measure the perpendicular this voltage. So according to our this geometry in XX and XY, we call in Y voltage, because this direction is Y and we flow the current in X direction. So, and when we convert this voltage into resistance, we call a Hall resistance, according to Ohm's law, which is very simple to apply. And when we measure such a voltage with magnetic field, so we found a linear behavior. So this linear behavior is also can be changed depending upon this material type. As I said, we have two type of material, magnetic and non-magnetic. So this behavior is totally non-magnetic material. When we measure a Hall voltage or Hall resistivity or Hall resistance with the variation of the field, so we have a linear voltage is depending upon the nature of the charge carrier. Suppose this charge carrier is p type or hole type, or so this voltage behavior is vary with positive slope. We have a negative charge carrier like electron, so this slope is negative. So by measuring the Hall voltage, we can say how and what type of charge carrier is inside the material. Not only type of the charge carrier, we can also calculate the density of the charge carrier. We can also calculate the mobility of charge carrier. How fast electron or hole is moving inside the material, which is this simple effect is very useful to measure the physical property of material, which is very common for like transistor. When we dope some and make a silicon in N type or P type, and how much we are doping, we can just and measure the Hall voltage or Hall resistance and calculate how much density is inside and how fast this electron is moving. So mobility is always responsibility for the performance of device. If you have a high mobility of electron, so it can give the high performance of the device. So we need the high mobility of material which give the high performance. So this is a simple experiment. This can change even when you change the material to non-magnetic to magnetic. So I'm going to show another effect, which is called the anomalous Hall effect. So anomalous Hall effect basically just a discover after 2 years of the basic Hall effect and parent Hall effect. So what will happen? We have two type of material, I said, magnetic and non-magnetic. Same, when we measure the same property, same voltage, same resistance in a magnetic material. So this behavior, this voltage is no more linear. So it will change the behavior of so this measurement. So what will happen? This measurement is look like such a non-linear behavior, not a linear behavior. But in non-magnetic material, this voltage and Hall voltage or Hall resistance is zero at the zero field. When you switch up the magnetic field, it goes zero in non-magnetic material in basic Hall effect. But when you apply such a thing in magnetic material, it changes the behavior non-linear into a non-linear. So there is two components inside the magnetic material. We can see this total resistivity, which is called the Hall resistivity, is the combination of ordinary Hall and anomalous Hall. So anomalous Hall, we can say this non-zero part at a zero field, we call a anomalous Hall. When we switch non-zero part, means when you switch up the magnetic field, we still have a Hall voltage, Hall resistance. So such a non-zero voltage we call a Hall resistance, so anomalous Hall resistance. But we have also a ordinary part like here. So we have also ordinary part. We can give you ordinary physical property of material, same as charge carrier density and mobility and type of carrier we can measure. So difference is only is that is so type of material. If you measure if you are measuring magnetic material or if you are measuring a non-magnetic material, the behavior of the Hall resistivity will change according to the but measurement geometry is same, and measurement geometry is always same. We just and measure the voltage perpendicular to applied magnetic field and current. So measurement geometry is same, only change is the type of material. And so third one is realized after a long time, like 100 years after, in 1980, is called a quantum Hall effect. So quantum up to 1918, quantum theory is well known for the physicists. So that's why it is very easy to discover a quantum Hall effect. But so what is quantum Hall effect? As we said, we have same material, we have different dimension. So difference dimension. So when we change the dimension, up to now I talk all the three-dimensional material. But when we squeeze one and squeeze the direction of the jet and make a lamella or thin film of gallium arsenide and the aluminum arsenide, and we call a two-dimensional electron gas. This is a very fundamental term in physics. We call a two-dimensional electron gas, but this is a thin film of gallium arsenide and gallium aluminum arsenide. So, and this material is very pure. We are able to synthesize when we make such a two-dimensional this device and apply a magnetic field and measure the same Hall voltage. So what we'll see? We see in Hall voltage. So this is material is non-magnetic. In principle, if this material is three-dimensional, it should behave a linear like a first one. But this material is two-dimensional, so it not behaving a linear. This behave like a stair. This blue curve is Hall resistance. So this blue curve is no more linear. It's behave like a stair. This step of the stair is depending upon the strength of the magnetic field. When we increase the magnetic field, step of this stair will increase accordingly. So when you this combined and measure this value of resistivity in term of E square by H. E is the charge carrier, and h is the Planck constant. So E square by h. So E square by h is also called a fundamental constant, and unit is the Ohm inverse. This unit is the conductivity. So we call a conductance or conductivity. So unit is Ohm inverse. So when we measure such a device, so but this is steps is like a is divided into 1, 2, 3. If you put the value of 1, so we start from highest and we go to this down. So it behave like a step. What is the origin of these steps? So let me start one movie here. Should be there, but is not what. Oh, here. So what is happening when we apply a magnetic field, a strong magnetic field in such a system, in two-dimensional system, all the valence band is quantized, again quantized. In three-dimensional balance, all valence band is filled by the charge carrier. But when we apply the magnetic field, this electron can again quantize this charge carrier and this density of the state. And again, and this quantize, which is responsible for such a effect. Like here, when you go to at the beginning, there is no magnetic field. Magnetic field is off now. So this is behave like a normal two-dimensional material. But when we start the magnetic field here, we can see the red dot. When we increase the magnetic field, we again quantize the valence band. So this quantization is very well known in physics, which is given by the Landau. So we call it a Landau quantization. So I mean this Landau quantization is responsible for this step-like behavior. So this step is very special, which is we can quantize in term of a this constant. And what is this constant? It is the E squared by h is the constant. And this effect is called this quantum Hall effect, because this resistivity is quantized in term of a universal constant E squared by h. So this effect is very robust. We cannot destroy this effect by destroying the geometry. Suppose we have such a device. When we squeeze destroy this device, but we retain the property of E squared by h always. When you squeeze more, so that this quantization is retained always. It doesn't matter how big is device and how is shape is this device, circular, so rectangular, so doesn't matter. This is independent of the shape of the device. We call this is a robust property of a quantum Hall effect. So and which is independent of the geometry. So this phenomena occur in presence of the magnetic field, but sometimes we don't have the magnetic field. So we call is, if we don't have a magnetic field, but we also see such a phenomena in special material. So we call another effect of the another version of the Hall effect. I'll show you later. So and so because that this previous property is independent of the geometry. So we have a independent of the geometry property. In mathematics we call the topology. So topology basically defined in mathematics, where if you change one shape of the material into another shape, it is their property will retain the same. Like here is cup of coffee is changing into a donut. According to topology, both this cup and donut have same property like a quantum Hall. It doesn't matter we have a square shape or we have a rectangular shape, but this quantization is always E square by H. So this quantization we call we also call a topological property. So in that previous effect is and awarded the Nobel Prize in 1985. So that effect is discovered by the Klaus on Klinzing, who is also director of the one of the Max Planck Institute. So in 85 he discovered this property in 80, but this Nobel Prize is awarded in 85. So that is the up to now this quantum Hall effect we discovered up to in two-dimensional system only. We can find another so direction where we easy to this confine the electron into two-dimensional. But recently some scientists found we can also do into a three-dimensional system. So like so zirconium pentapluoride is a special material where electron is moving very fast, and we can also do this. We do measure the this effect where we can see here this XY voltage we call the Hall voltage, which is represented by blue curve. You can also see similar to step-like behavior. So, but this step, when you calculate this value of this step, so this step is not same as a step of the two-dimensional system. This step can be quantized by the size of the Fermi pocket, because here so material is three-dimensional, but we have to do some extra mathematics to quantize it. So here is E square by H, H by E square is there, but extra term is here is also a Fermi vector, Fermi wavelength. But in two-dimensional system, it's very easy to do only in E square by H or H by E square. This depending upon this value of resistivity. We are measuring resistivity or we are measuring this conductivity. So if you are measuring resistivity, which is the inverse, some time of some sort of the inverse of the so conductivity. So in resistivity, we have H by E square in resistivity. When we call it conductivity, we have E square by H, just inverse of the this value. But in three-dimensional, it's not easy to quantize, but we are still looking many more material how to do this perfect this quantization in three-dimensional system. I mean, when we change the dimensionality of the system, we change the whole property. I mean, so it is well known this quantization is always occurred in low dimensional system and even in low temperature, because this quantization, so this quantum phenomena is always a low energy phenomena. Low energy phenomena means this temperature is always defined in terms of energy. So we can see still we have this measurement at 0.6 Kelvin. When you go to more temperature, all these property step is gone. We have a linear behavior, like a first observation, where we only see a linear behavior with magnetic field. But when we go to lower and lower temperature, when quantization occur and this quantum phenomena occur, so we have a sort of some step like behavior where we can calculate the value of the step. I mean, it's low temperature and sometimes high magnetic field and sometimes special and this material, we always need to see such a this phenomena, this quantum Hall. But after some year, and scientists also found that this step is a step up stair is not a only one step. There inside is many steps. Like earlier in the beginning of the school year, we thought that like electron and electron and proton is only particle inside the nucleus and neutron. But after some time in higher education, we also know this electron proton is also in term of this gluon. So we also that know some we can also divide this elementary charge particle into some other sub charge particle. So similar here. So depending upon this quality of material, if you have ultra pure material of this same material, then we can see in between some more step. When we see such a more step inside, so we call it fractional Hall effect, fractional quantum Hall effect, because we earlier see the steps in the straight line. We can see it, some of the step. Here is the bigger step, and in between, like this is the first step, but in between we saw many steps. So we can see 4, 3, 2, and 1 is here. So these are the number of steps like a first one, but in between we see a many small steps. So these steps we can also measure value of. So this step in term of n is the integer, which one is called the normal quantum Hall effect. But this step you can factorize into p and p plus q, and p and q are the again integer. So these values are very special. We cannot take all these value p and q value of integer. We can take only some special value are allowed only. We can see here 1/3 and 2/3 and 4/3. Such a number only allowed in this to see this step. So such a this phenomena observed by the first time in Laughling by his colleague, and also got the Nobel Prize in 1998. So again we have a fractionalization of the this quantum Hall effect, but up to now all the Hall effect is governed by the charge carrier, not the spin of the electron. But we have also some spin inside the electron, as I said in first PPT. We have also, when we are able to measure the spin of the electron, so we call a spin Hall effect. Same measurement, but we need a special device. So what is the special? We just deposit some magnetic element on the top of the gallium arsenide. So gallium arsenide is a similar system, which is the non-magnetic, but we have to deposit some and this magnetic system like iron on the top of the this gallium. So what happened? This iron filter out the spin of the electron. We know the spin up and the spin down of the charge carrier. When we are able to measure such a device, then we can only measure the spin of the current, not a charge so current. Here is the voltage is always perpendicular, as I said, like a normal Hall, but we have some extra device where we can measure the voltage, and where we can only observe the spin current of the electron, not a charge this current. So this phenomena is only governed by the spin of electron. That's why we call it a spin Hall effect. So there is another version also, quantum value of spin Hall effect. When we introduce like a previous one, we have Hall effect, but we have also quantization of Hall effect. In similar way, we have spin Hall effect, but we have also, we observe spin quantum Hall effect or quantum spin Hall effect in later 2017. So what will happen? We have a special material and make a again this quantum well of such material, where we don't need any magnetic field. We just measure the this voltage perpendicular to this current. We got the 2 times of the E square by H. Earlier we have only 1 electron, but here we have 2 electron in a channel. So here we got 2 times of the this value without apply any magnetic field. So this phenomena is occur because this value is quantized due to spin. So that's why we call a quantum spin Hall effect. That is occur without magnetic field. We don't need any magnetic field, but still we are measuring perpendicular voltage. That's why we call it Hall voltage, and this occur due to spin. So we call quantum spin Hall effect. But what is the origin and what are the material where these people recognize this this effect? So we have cadmium arsenide and this mercury, this cadmium tolrite and mercury tolrite. These are the 2 special material. But when you see, these are material is a semiconducting. One is a normal semiconductor. We have a inverted semiconductor. Inverted semiconductor means like a silicon, germanium. We have always S band is a conduction band and P band is always a valence band. This is the normal semiconductor. But when we go to higher atomic number means heavier element. So this S and P will be reversed due to spin orbit coupling inside. We have a spin of electron. We have also orbital this motion of electron that will change the band structure of the this material. So when you compare the band structure of this cadmium tolrite and mercury tolrite, so we found one is we have like a silicon, which is the normal semiconductor, and one is a inverted semiconductor. So when we make a device of this size, 6.3 nanometer of this this sandwich of mercury tolrite, so we can see this this effect of the quantum spin Hall effect. So what is the origin of this magnetic field? I said spin Hall effect is occur only in without magnetic field. When we where the source of the origin of the this magnetic field. So as I said, we have spin up electron, and electron is always moving this surrounding the nucleus. So that is create spin orbit coupling by LS coupling, IJJ coupling, depending upon the this type of this coupling that create the energy, that create the force, that create the electricity, electric field and magnetic field. So depending upon electric field and magnetic field, depending upon the observer frame of reference, we call the observer. So if you are so observing so effect of LS, this coupling, spin orbit coupling by nucleus, inside the nucleus, so we call is a electric field. But when we are in the this moving observer like electron, when we are sitting on the electron, we feel as a magnetic field. Just such effect of LS, this we feel as a magnetic field. So I mean, in electron is always feel a magnetic field, but that is magnetic field. In nucleus always feel a electric field. This is the frame of reference of the observation. So thus value of electric this LS coupling is depending upon the this number of atomic number power 4. So I mean, when you go to lower atomic number to higher atomic number, we have more and more spin orbit coupling, more and more stronger spin orbit coupling. That's why in previous slide, mercury thorium has less spin orbit coupling, but cadmium thorium has less spin orbit coupling, but Mercury, thorium has high spin orbit coupling because of mercury has higher this atomic number in comparison to cadmium. So in spin Hall effect of spin Hall effect or quantum value of spin Hall effect, we always used to see in higher atomic number, not in lower atomic number, this compound. And last one is quantum anomalous Hall. We have a Hall effect, quantum Hall effect, but in earlier in 1881 we have also anomalous Hall effect, but we didn't see this quantized value of anomalous Hall effect. But theory is well developed now in 2030 after this discovery of topological insulator. So we also call spin Hall effect is quantum spin Hall effect is two-dimensional topological insulator. But when we have such a topological insulator, when we just dope some this magnetic element inside, and when you dope magnetic element, as I said, in the anomalous Hall, we always observe in magnetic compound. But when you see in a thin film, like a two-dimensional system, we always see a quantum the value of the this anomalous Hall effect. This quantum value also quantized in term of h by e square or e by e square by h in term of conductivity. So such a system or such a phenomena just discovered recently in 2030. But there is some more phenomena is happening in three-dimensional system. How do we find in three-dimensional system? As I said, all these quantum phenomena occur only in low-dimensional system, in two-dimensional system, for example. But we try to find such a phenomena in three-dimensional system. How we can do? So an anomalous Hall is always occur in some this magnetic compound. So we have some three-dimensional system, but this magnetic spin is only responsible for the anomalous, and other charge carrier doesn't responsible for anomalous. So what we'll do, what we can do, we just distribute. We have three-dimensional system, means bulk. We just distribute each measurement into a number of layer of this magnetic layer. Suppose here is one system is this cobalt 3, tin and sulfur. Only cobalt is responsible for the this magnetism. We see a huge value of anomalous Hall, but we want to do quantization. How to do quantization? We just all measure value, we distribute all over the each number of this magnetic layer. Suppose each this magnetic layer, we know the unit cell, we know the separation of the this magnetic layer. Just we divide it. Divide means distribute it all over this sample or this compound. So when you do that, so we just divide all the measurement into a number of layer in the system. We found that each layer is almost this contributing a quantum, this value. So in three-dimensional, we try to found. This is not a very justified. Still, we are working. We can see here in 2021 we published one paper regarding this in three-dimensional quantization of three-dimensional the anomalous Hall effect in magnetic system. So we have many more magnetic system. One is here also example, manganese, aluminum, gallium, where is the only one manganese magnetic atom. When we measure a bulk system, we don't need thin film, just distribute all this measurement into each number of layer. We know the unit cell, we know the dimension of our sample or our measuring compound, and we divide the unit cell in each unit cell, we know the how many magnetic layer is there. So we calculate the how many numbers of magnetic layer inside our whole measuring this compound. We just distribute. We are able to find each this magnetic layer is this contributing a quantum value. Like in a perfect quantization, we have a thin film, like only one layer of the magnetic layer. So similar to that way, we can also distribute in thin dimensional system into a each number of layer. And there is some more, hopefully there is a already prediction is we can also see some fraction value of quantum anomalous Hall. Not only this quantum value, we can see fraction value like this fractional quantum Hall. We can also able to see this fractional quantum Hall. This is the assumption. This is the our motivation to do, but nobody did it, nobody found it. That means we need some special material. What type of material we can see such a phenomena? So we have a very special, like in anomalous, we have the ferromagnetic material, but we have also a where the spin is not aligned in perfect direction, and we have such a spin where is the surrounding in a like a circle. This is not in only one direction, is moving in a some geometrical way. So such a system we have, we call it magnetic Skarmian. Like in a magnetic system, we have a magnetic domain, like a ferromagnetic domain, one where in one domain all the spin are aligned in one direction. But magnetic Skarmian is not a such a system. This is a different system, different material, where the spin are randomly going in some other in a so very special sort of direction. So such a system we have. We also realize in such a system in Lorentz microscopy, where we can see the orientation and all the direction of the spin in Lorentz transmission is microscopy. We can see in each bubble, when we zoom it in each bubble, we see such a spin orientation. So it might be such a system you need to choose to realize such a fractional the anomalous quantum Hall effect, where the spin is not only aligned in one direction, but it is aligned in some special direction. Only some part of the spin only able to contribute in the anomalous value, not the this perfect. One spin is able to contribute if perfect. One spin is contributing, so we call it a perfect anomalous Hall, this quantum anomalous Hall. But in some part, some fraction value is contributing, we call a fractional quantum anomalous Hall. So such a system and such a phenomena we are still looking, but nobody knows where it will be going to discover. So this is my last up to now. I said the whole story of the this Hall effect. I hope you understand something more, and if you have any doubts or any question, I'm happy to answer it.
Thank you, sir. I extend my hearty thanks to Dr. Chandra Shekhar for this informative talk and very elaborately explaining the journey of Hall effect in magnetic and non-magnetic materials. He explained the role of electron as charge as well as spin, also different dimensionality of materials and how we can stimulate their properties. He also explains quantum Hall effect and fractional quantum Hall effect, spin Hall effect in a very interesting way. Thank you, sir. Now for the question and answer session round, I would like to hand over to Dr. Ashwini Kumar Singh, sir. Over to you, Ashwini, sir.
Am I audible?
Yes, sir, you are audible.
Okay, questions? Questions are asked from audience. Please, you can, if you have any query, you can ask your questions. You can type in your message box.
You can also unmute and just talk
either you-
about any chatting. Or you can also chat. I can see chat list. One question from audience is that how you choose the bulk material for the anomalous spin Hall effect. The anomalous spin Hall effect is the another version we expect it will come in future, because a spin Hall effect is discovered. Quantum spin Hall effect is already discovered, but fractional spin Hall effect is not discovered. But this is anomalous spin Hall effect is we can choose a material with example like a topological insulator. So topological insulator is one is such a wonderful material which was discovered in 2006 through a spin quantum Hall effect. So for this we have bulk is insulating, but surface is conducting. Surface is not only conducting like a gold or some steel or iron. So surface is a very special conducting. When you measure such a surface, or ideally such a surface, so we can see only quantization of, well, 2 electron is going, one is spin up and one is spin down, only one channel. So that is a surface which is always give you a quantized value if you are measuring perfect. But problem is that we don't have a ideal material. We can imagine we have a 3-dimensional system like a cube, where when you pass a current in such a system, and current is independent, and current is always go through the smallest resistivity path. So smallest resistivity path is the surface, which is metallic, but bulk is not totally or 100% insulating. Some current is always leak through. We can say so some fraction of the current is leak through inside. So that is not going to be perfect this quantization, but we reach at least 90% of this quantization, but not 100%. But ideally it's not 100% possible like a quantum Hall effect and like a spin in quantum Hall effect. But in low dimensional is possible. Low dimensional is possible because there is no bulk inside. If you squeeze this cube into a plate, so you dismiss the one direction. That means only surface is there. So in form of a thin film, we can realize in such effect. So there is many more question inside. How to read it?
I will read it.
I will read it out, sir. And another question is, why is Hall measurement for the carrier concentration performed under a vacuum? No. Who
Sir,
said this carrier concentration can be performed only by code? You can perform anywhere in the atmosphere also, in open atmosphere, but we need a magnetic field. So to apply a magnetic field,
Monica ma'am. Sir, एक minute. Oh, Monica ma'am, Partha sir want to ask some question. He has
Yeah,
raised his hand.
yes, sir.
Please
One
unmute.
of our senior faculty, Dr. Partha sir, also
Yeah.
wanted to ask a question. So you are unmuted, sir. You can unmute yourself.
okay, chat this question I will answer later.
Partha sir, you can unmute yourself.
Hello. Am I audible?
Yes, sir.
Yes.
Yes, sir. You are audible.
Chandra Shekhar, I would like to ask you one question. You spoken about QSH, quantum spin Hall effect, and quantum anomalous Hall effect, right? Hello? Hello?
Yes, sir. He is listening you.
Are you listening?
Yeah.
Yeah.
I'm listening. Yeah.
Okay. So, I would like to point out that for the first, that is for QSH, one should have stressed on the fact that time reversal symmetry is not broken. On the other hand, in QAH, quantum anomalous Hall effect, time reversal symmetry is very much broken, right? And secondly, in both the spin orbit coupling, be it Rashba coupling, be it Dresselhaus coupling, if the host material is of zinc blend structure, so such coupling strengths should be very strong. In fact, Kane and Milley in 2006 had predicted that graphene could be a quantum spin Hall insulator or something like that. But graphene, unfortunately, has SOC, spin orbit coupling, very weak. One can, of course, augment it by putting graphene in a substrate of, let us say, transition metal chalcogenides, TMDs, and all that, which have very strong spin orbit coupling, constructing a van der Waals heterostructure. So such things are possible. So I believe this particular point should have been very pointedly emphasized. I have been working in this field for a very long time, and I find that students really, those who are working really, they get stuck up somewhere in between QSH and QHA. So, and this is the point of difference, which I, in my humble comprehension, I find that the exact point of difference is unbroken time reversal symmetry in QSH and in QHAH, broken time reversal symmetry. I think what I'm saying, you would agree with that?
Yeah, actually, you are 100% right, sir. And the difference is only time reversal symmetry. So in anomalous Hall, in quantization anomalous Hall, we break time reversal symmetry because we need to apply magnetic field. Okay, so magnetic field is always break time reversal symmetry. So if you break time reversal,
or magnetic impurities, impurities.
Yeah.
Or
magnetic field. So I mean, magnetic field means are external or internal. If you have a magnetic element, so that also break time reversal symmetry. If you are applying externally magnetic field, that also break time reversal symmetry.
Yeah, sure.
So what happened inside? What happened with the electron when you break such a symmetry? So that create a extra path where when you doesn't break, so all the one is like inside, one is external, one is internal. So I mean, one is extra field is SOC. SOC means spin orbit coupling, which is internal magnetic field. So internal magnetic field doesn't break, but separate the spin. Where spin up has one quantum of energy, and spin down has one, so different quantum of energy. Two are quantum of energy means two spins have two different channel. They are not going in same path. They are different channel. That's why always spin quantum Hall is giving value of 2. Instead of anomalous Hall is giving the value of 1 prefactor. So prefactor means E square by H is 1, and but spin
that is called Kane-Billy index. Z2 Kane-Billy index. Z2.
So in quantization, we can separate. If you are measuring 1 E square by H, that means it is coming independent of the spin of the electron. But we are measuring two value of that. That means both spin are contributing independently. Both are going in two different paths. That's why we are measuring two value of this quantization. This is the basic difference in measurement or in measuring value.
Now, talking about, while we are on internal field, I would like to bother you with another question, which I have not yet worked on, but I think people all over the world are very interested, particularly condensed matter people. That is a problem concerning Kagome lattice. It has a non-trivial geometry. You agree? And it can host diverse quantum phases.
Yes.
And including anomalous quantum Hall effect possible. But have you been, or has there been any direct evidence of TRS breaking, time reversal symmetry breaking in Kagome lattice? So I have not been able to find.
This actually Kagome compound, there are two family. One is magnetic, one is non-magnetic. But lattice is this Kagome.
Yeah, take for example AV3SB5. AV3SB5. This type of.
So this one is non-magnetic, but there is a spin charge density band. Density band of 95 Kelvin.
I think there is chiral charge order. I think there is chiral charge order.
That charge density band is vanadium is responsible for that. So because vanadium is sitting on this Kagome lattice.
So there is no direct evidence of TRS breaking yet. But do you know, has anyone shown that TRS breaking indeed is occurring out there?
Yeah, so if you have another family of this Kagome lattice, we have, for example, yttrium, magnet 6, tin 6. This is this 166 has hundreds of the compound, which is also this Kagome. We are able to replace first element is all rare earth element or first block element, first the group of element, and in the middle in manganese we are able to this first row of transition the magnetic element, and third one is tin. We are able to replace even germanium, silicon. There is many versions. All are compound form this Kagome, which break the time reversal symmetry due to magnetic element.
Okay. Thank you very much.
Thank you. Thank you.
Okay, so next question from Hira Joshi, and that is, what are Skarmians? So I would like to answer you.
Fermion is
Skarmians, sir. Skarmians.
Skarmian is also particle like a fermion, but this is composed of a this spin. So like that spin have there is many type of skarmion, which is we also call a fermion particle. So in particle physics, when you go to high energy physics, there is many more. Wild fermion, Dirac fermion, and also in spin we have a skarmion, which is behave as a particle. So that's a collection of spins, which one I showed here in the my PPT, if you are able to if this is visible. So this collection of the spin, such a collection of spin which behave a particle, which is similar property of fermion, but this is the collection of spin. They have also charge plus minus, and also exist in many variants. This is the simple one I wanted to show you, but this is anti-Skarmian. We have block Skarmian, and we have double Skarmian. There is many type of Skarmian, but Skarmian is behave like a particle, like a fermion. I wanted to say.
Okay, so next question is from Dr. Vikram Verma, sir. Can Hall effect be observed in one-dimensional materials, such as material in form of wire or quantum wire, probably?
So Hall effect or quantum Hall effect. Hall effect you can observe any material. So because Hall effect is measure only charge carrier, so deflection. If you have charge carrier inside, so in principle every material have some charge carrier inside. So that so deflect due to Lorentz force. Then we have a non-zero voltage perpendicular to the magnetic field and current. So it doesn't matter the this dimensionality of the material, Hall effect especially. But when you want to go in quantum level, but then we have to reduce this dimensionality, because quantum phenomena is always occur in low dimensional system. When like a quantum well, we know quantum well, where and we can quantize the energy, and also in low temperature. So because energy of this quantization is very low, and energy is always we measure in terms of temperature. So all these quantum phenomena occur in very low temperature, in millikelvin, millikelvin, or some sort of order of 1 Kelvin, you can say 4-5 Kelvin. But when you go to high temperature, it will destroy due to thermal energy. Thermal energy means again in terms of this value of K and T. T, when T increasing, we increase the thermal energy, we destroy this quantum property. So Hall effect we can measure in any system, doesn't matter.
Okay, sir. Next question is from Rita Singh, and she's asking that why some metals have positive Hall coefficient while charge carriers are electrons.
Which one? Can you say again?
Why some metals have positive Hall coefficients while the charge carriers are electrons?
Some metals.
Yes, some metals.
Some metals, if we have, so is so and also if Fermi surface is asymmetric. So I mean all these properties governed by the Fermi surface. If that metal has some asymmetric Fermi surface, so in one direction we measure like a P type, and but another direction must be N type. This depending upon this curvature of if the curvature of the Fermi pocket in measuring the direction is negative. So we have a electron type this behavior, but this curvature is positive. So we have a hole type behavior. So this question is valid in asymmetric Fermi pocket. But if you have a symmetric this Fermi pocket like a this copper, so we always measure a same charge carrier, which is electron. If this Fermi pocket is combined with electron, so we always measure n type of charge carrier, which is which represent as an electron. So I mean p and p type and n type is also is depending upon the type of Fermi surface sometime, and this effect is called bipolar effect. If two different direction is giving two different type of charge carrier, this called is bipolar. So that might be happen in such a material.
Okay, next question is from Dr. Yogesh Kumar. He is asking that whether is it possible to decrease Hall voltage when magnetic field is increased? Is it possible to decrease the Hall voltage by increasing magnetic field?
By increasing magnetic field, we want to decrease magnitude. We cannot decrease, but in quantity we can decrease. Quantity means if you have negative value in electron type of system, so total value when you start when you go to high magnetic field, we have high negative value. But when you this high negative value means lower value. But when you call a magnitude without taking the sign of positive and negative, so it is not possible to decrease it, because Hall voltage is proportional to magnetic field.
Okay, so the next question is that Amit Kumar has asked this, that what could be the possible base to realize the experimental fractional quantum anomalous Hall effect?
Can you say first word? What
is the possible base? Means how we can predict for some material like magnetic element hoga ya other element it will be, or there will be some exchange to realize the experimentally fractional quantum anomalous Hall effect.
Fractional. Let me see.
Yes, this one.
Fractional quantum anomalous Hall.
Yes. So how we can realize that? I mean, how we can predict which material will be?
So I propose one system like Skarmian, where spin are very in fancy way, not a like a this spin are not like a ferromagnetic where spin are totally aligned. But in a Skarmianic system, spin are not totally aligned in one direction. This is some special arrangement. So we need, as we know, if magnetic spin are aligned like a ferromagnetic system, so we can see only a quantum anomalous Hall. We cannot see a fraction. We cannot see in a fraction value. But if we have a spin in fraction value, because in one spin is responsible for the this quantum anomalous Hall. So we think that this is my motivation in my my assumption. If you have a fraction of spin, then we are able to realize this fractional quantum Hall effect. Otherwise, if you have a fully aligned spin which contribute 1, so that system we always used to observe a quantum anomalous Hall, not fraction one.
Okay, sir. Yes, finish, please. Okay, so Aryan Khare has asked question that why Hall coefficient increases with decrease in number of charge carriers? Hall coefficient.
So actually, when you see the formula, So Hall coefficient is measured by the slope. Let me go to first slide where the linear was there. When you see here, so Hall coefficient we call the slope of the line, P type or N type. Thus slope. The slope means Hall resistivity divided by field. So this is called the Hall coefficient, and this Hall coefficient we call RH, and RH is related to 1 by NE. N is the charge density and E is the electronic charge. So this is the inversely proportional to number of charge carrier. Okay.
Okay.
So Hall voltage means Hall constant, and Hall constant is inversely proportional to charge density. If you have larger charge density like a copper, so we can see lower value of Hall coefficient. If you have a silicon like a low charge carrier density, semiconducting compound, silicon or germanium, we have high value of this Hall coefficient because this is inversely proportional to number of charge carrier.
Okay, sir. We have a question from a very senior professor, Dr. S.M. Jha, sir. And he want to ask that what is the perspective of Hall effect in 2022 and in future?
The perspective of Hall effect, as I said, we are still looking many more phenomena. We have done already charge and we have done already spin. So electron has two things, charge and spin. We already took account of charge and spin. We found this, we reached already quantum Hall effect due to charge. And we already reached quantum spin Hall effect due to spin. But we are still looking some fractional value of spin. If we are able to contribute some fractional value in current, then we are able to observe this fractional, this quantum anomalous Hall. That one we have hope this will be a future, but we need some more and more justification how we can reach a fractional spin and how and which device is we are able to observe. So there are many parameters we have to look in this respect.
Okay, let me summarize this question answer session by putting my question also. As you
can ask on WhatsApp even.
Okay, you told us that this quantum Hall effect we can observe only at very low temperature. It is a low temperature phenomena. But what is the reason that graphene, in graphene, that is pure 2D, say monolayer of graphene, we observe this quantum Hall phenomena at room temperature?
Yeah. Okay. So that is the good this question. So because this graphene is ultra pure material which exists in 2-dimensional, only exists in 2-dimensional. This is the single layer of graphene the graphite, which is called graphene. So this is ultra pure. So we have a mobility, ultra fast electron, which exists even at room temperature. If we compare ultra fast this electron velocity of any other like a gallium arsenide, this quantum well at room temperature, this electron is going to dismiss, which is very slow at room temperature. So I mean, once we have a ultra fast electron like a graphene, even when you see the value of this mobility of graphene at room temperature, this is still 1,000 or 10,000 of the unit. But when you compare this this mobility of such an electron in other system, not in graphene, this might be in 100 are tens of the numbers. So I mean, once we have this fast moving electron, so we are sure able to measure this quantum phenomena up to that level of temperature. This is the this mobility is always depend upon this quality of sample and bind structure of the material. So one parameter is and mobility, which control this phenomena of the quantization. So this is the yeah, my answer, which is I know all this phenomena is governed by the this mobility or fast moving electron. If you have all the device what I showed you here, which showed this quantum phenomena, when you make a polycrystalline, when you make a powder and make again sandwich and measure, all the phenomena will destroy, because mobility of electron is not exist in high level. This is already destroyed. So one is only one parameter is mobility. If you are able to control mobility up to high temperature, then still you are able to measure.
Okay, sir. Thank you for answering all the questions very patiently. Now I hand over this session to Monica ma'am, please.
Thank you, Ashwini sir, and thank you, Chandra Shekhar sir, for giving the answers to all the questions. Now I would like to invite the convener of Physics Society and our respected Dr. Pankaj Singh sir to give the vote of thanks. Over to you, sir.
Thank you. Thank you, Monica. Am I audible?
Yes, sir, you are audible.
Am I audible, please?
Yes, sir. Yes, sir.
Hello.
Yes, sir, you are audible.
Yes.
Hello. Hello.
Yes.
Hello.
Sir, you are entering from two devices, I think. That is causing the problem.
Now am I audible? Yes, hello.
Yes, sir.
Thank you, Monica, for providing me this opportunity. And good afternoon to all of you. On the behalf of the Physics Department, Physics Society of Deshbandhu College, I thank Professor Chandra Shekhar sir for explaining the never-ending journey of Hall effect in a various simple language with the help of live examples. Despite being associated with such a world-famous institute as Max Planck, Professor Chandra Shekhar took time for our development and mental upliftment. I thank respected Professor Chandra Shekhar sir for the bottom of my heart. At the time, I thank Principal Deshbandhu College, respected Professor Rajiv Agrawal sir, Vice Principal Professor Kamal Gupta sir, IQAC Coordinator of our college, Dr. Aditya Saxena, DBT Star Coordinator, Dr. Indrakant Singh, and the head of the Department of Physics, Dr. Kakoli Bera, for taking initiative to organize the program. In the next step, I am grateful to
It might be we lost connection.
So you are muted.
Pankaj sir, you are muted actually. You have muted yourself.
Yes. In the next step, I am grateful to all my colleagues from Deshbandhu College and other colleges whose eagerness and presence has blessed the program today. How can I forget the non-teaching staff of my college and my
Recording in progress.
I'm audible?
Yes, sir. Yes, sir.
How can I forget the non-teaching staff of my college and my loving little scientist, that is our student, who's adorned this program with full discipline and curiosity. Last but not the least, thanks is due to the technical team of our colleague for this full support during and before the session. In future, with the cooperation of all of you, we will continue to organize such program regularly. This hope I stop my words. Thank you very much, sir. Over to Monica.
Thank you, sir, for your vote of thanks. I think the session can be closed now. Thank you, everyone.
Thank you. Thank you very much.